Tamam, başlayayım o zaman ben.
All right. Okay, the stage is yours.
Okay, thanks. So, okay. Thank you very much for inviting me to give a talk here at this school. So I'm going to talk about the Witten index and its applications. So since it's for undergrad students mainly, I'm planning to give some motivation in the second lecture, actually not now, because I need some sort of algebraic and some mathematical tools in order to give really the really interesting sort of, or somehow more theoretical physics side motivation of the Witten index story. So today I'm going to talk therefore I'm going to talk about Grassman algebra and the so-called coherent states. I'm sure some of you know these notions from quantum mechanics, but still let me just very briefly explain what's the Grassman algebra, what's the Grassman numbers, and then what's the coherent state. Okay, so again, the plan is to talk about the Witten index, okay, and its applications. So the applications will be the last lecture, but what's the very roughly what's the Witten index? So in supersymmetric theories, we want to check if very roughly if supersymmetry is spontaneously broken or not. And there's such a rule, such a tool as a Witten index, so-called Witten index. It's some topological invariant. So this can help us to tell if supersymmetry is spontaneously broken or not. Okay, so one needs to compute this index, and just if you know what's that index, then you can say something about supersymmetry. But this is just very roughly. Of course, then you can use this index for many things.
Is it possible that you have forgotten to share your screen? Or...
Okay, sorry, I am talking, but yeah, thanks. I actually opened, but thank you very much. So actually, I haven't started to write, so it's fine, but still, thanks. So, okay, now, the plan is to compute this Witten index for supersymmetric quantum mechanics, so and show its properties. But for that I need to explain what's the Grassman algebra first. Okay, so let me start. This is the first lecture. It's about the Grassman algebras, and later I'll talk about coherent states. Okay, so the lecture first, it's about Grassman algebras. So again, it's very rough, a very quick introduction to Grassman algebras. I'm not going to talk really about the algebra, but just show you the properties of these Grassman numbers. Okay, so what we call Grassman algebra, if we have some generators in the algebra, let me call them theta I, okay, which satisfies this commutation relation, or actually we call this anti-commutation relation. Okay, so it's theta I, theta j. This is anti-commutation relation. Which means that it's just theta I. So I runs from 1 to n. So theta I, theta j plus theta j, theta I. This equals to 0. Okay, if I is not equal to j. So this is this we called Grassman algebra. So we have some generators and we have such a anti-commutation relation. Okay, so in particular, so for theta I, you can see that for theta I, what we get, it's theta I plus theta I, and that equals to 2 times theta I square, that equals to 0. So this particularly, so for Grassman number theta square equals to 0. Okay. Now, in our constructions, I will use only, so maybe I'll talk a little bit about the case where we have 2 different Grassman numbers, but mainly I'll talk about the one, or I'll talk about the complex Grassman number where we have complex Grassman number and its conjugate. Okay, so now in case if you have just one Grassman number, so theta in our algebra, just one theta, so it's example. What we can do, we can consider all functions in this algebra. So let's say that we have just theta. Okay. So then let's consider some function f of theta, and we can Taylor expand this function. Okay. And this is some f, some constant, so 0 plus. Let me write zeros in subscript. Okay, so let's expand this. So this is Taylor expansion. And then f theta is just equals to f0 plus f1 theta plus f2 theta square plus theta square, what, 2 factorial. Okay, that's matter. So and so on. Okay, so since this is theta is Grassman, so that means that theta square equals to 0. So starting from the from theta square, all these other terms equals to 0. Okay, because theta square equals to 0, cube equals to 0, and so on. Okay, so as you see, all functions in if you have just one Grassman variable theta, so all functions has this form, so that f theta equals some f0, this is some constant, okay, and this is also f1, also some constant, and then theta. Okay, then now one can construct, if you have 2 thetas, so 2 Grassman variables, then you have one quadratic term, and so on. You can continue, you can do this for the case where you have 3 different Grassman variables and so on. Okay. So now just maybe I can show another example. So if you have 2 thetas, then it's easily just theta 1, theta 2. And so what we know is theta 1 equals to theta 2 square, so it's equals to 0, and theta 1, theta 2 equals to minus theta 2, theta 1. So because of this relation, because of this first relation, okay. So they are anti-commute, okay. Now f theta 1, theta 2, it's just f0 plus f1 theta 1 plus f2 theta 2 and plus f3 theta 1 theta 2. Okay, so this is some constants here. So all these guys, some constants. So this is the general form of any function if you have 2 different Grassman variables. Okay, so you just Taylor expand and keep only quadratic term until quadratic term. Of course, here again you can add theta 1 square, theta 2 square, other things, but all of them are equal to 0. Okay. Now, what's important for us to do some analysis here. For instance, we want to know how to differentiate these functions, how to integrate them. So differentiation, since we have, you see, anti-commutation, it's important to define how we take the derivative from the left-hand side or from the right-hand side. Okay. Since, again, if you have such a term, theta 1, theta 2, and then let's say that you want to take the derivative d theta 1, okay, so let me partial dd theta 1. So you see, if you act with this derivative from the left-hand side, sort of, then you just get theta 2 as a result. But if you do with right-hand side, then you need to change theta 1 and theta 2. That will be theta 2 minus theta 2 theta 1, and then it equals to minus theta 2. Okay, so just let's just define left derivative. So I will never use any subscript for that, but so this will be our notation. So whenever I take the derivative, that's just left derivative. Okay, so if you have such a function f theta 1 theta 2, and if you take dd theta 1, for instance, that means that, so again, this dd theta 1, here we have f0 plus f1 theta 1, f2 theta 2 plus f3 theta 1 theta 2. That equals to, so the first term is just 0, then another term gives f1, and then the last term gives just f3 theta 2. So the derivative dd theta 2, yeah, it's just again f2, but when you come to the term to this term dd theta 2 f3 theta 1 theta 2, here we need to change this the order of theta 1 and theta 2, and that gives f2. So one needs to change the order. It's minus f3 theta 2 theta 1, and then it's just f2 minus f3 theta 1. Okay, so this is how we differentiate. Okay. So now about integration, the most important stuff here, because later we'll use this for the path integral in order to compute the Witten index. So in integration, we define the so-called, so actually this so Grassman algebra, of course, it was known much before. Then Berezin introduced this super symmetry story, but still the analysis of the structures was introduced by Berezin. It was, I think, before 70s, before introducing supersymmetry and supersymmetric quantum mechanics. So in the 60s, Berezin introduced the so-called Berezin integration. Okay, so it's Berezin integration. That means that if you want to integrate over the Grassman variable, what you do, you just take the derivative. So it's just if you have some d theta, so that's just taking the derivative. So this is how we integrate here. Okay, so this is the rule. So this is important. So of course it depends how you want to define the integration, but here you can easily check that it satisfies many properties of the normal integration, which we know from the real analysis. Okay, now maybe I can show just one example where we can compute some integral. So let me write some exponential function. So some example. So the exponential function, again, let's say that we have two Grassman variables, theta 1 and theta 2, and let's define some exponential function. So so it's just e to the theta 1 theta 2, for instance. Okay, you can put minus here like in Gaussian integral. Okay, Gaussian expansion. Now so now we can Taylor expand this. So if you Taylor expand, so maybe sorry, let me write just some coefficient here also. So let me write here some coefficient. So it's c theta 1, theta 2, okay. And then if you expand this gives just 1 here. It's 1 theta 2 equals to 0, and then it's minus c theta 1, theta 2, and all other terms it's just quadratic into the quadratic in theta 1, theta 2, okay. So it's all equals to 0. So this is our exponential function. So it's just 1 minus c theta 1, theta 2. Okay. Now we want to integrate this exponential function. So what happens here? So it's important, to keep the order. So let's write d theta 1, d theta 2. So this is Grassman variable, so they're not commute with each other. So okay. So now d theta 1, d theta 2. Now e to the minus c theta 1, theta 2. Now this integral equals to d theta 1, theta 2. And here it's 1 minus c theta 1, theta 2. Okay. Now taking this integral d theta 2, it means that taking just derivative. Okay. Now this gives d theta 1. And here it's just so in order to take this derivative, so one needs to change this theta 1 and theta 2. So that gives just plus c, okay? So plus c theta 1. And then integration over theta 1 is just taking the derivative. And this just gives c. So this integral, for instance, say this integral just equals to c, okay? So we will consider similar integrals, okay, later. So now what you can do, so this maybe I can ask you to do yourself. So just, so you can try to compute some Gaussian integral here. So it's just, let's say that d theta I so maybe so since we will use complex one, so let me just introduce the complex one. So so the complex Grassman variable, it's just, let's say that we have theta 1 and theta 2. It's real Grassman, okay, variables. So by real, what I mean that theta bar equals to theta, okay? So this is what I mean by real. So now we can introduce now complex Grassman variables. So it's just, let's say psi, it's just 1 over square root of 2, theta 1 plus e theta 2, and then psi bar, it's just 1 over square root of 2, and here theta 1 minus e theta 2, okay? So this is, let me, the homework, try to do yourself. Now what you can do, you can compute such an integral. Let me write, so this is so let me write this in this way. So let me write this in this way, theta 1, so it's psi 1 bar d psi 2 bar d psi n bar, and then so again here d psi 1 d psi n, okay, times now e to the minus psi. So maybe I need to write, it's better to write summation. So ij from 1 to n, and here psi bar I. Let me write here some aij's. This is antisymmetric matrix. So let me just write psi j. So just try to compute this integral and see what you'll get. So this is Gaussian integral, but in Grassman variables. Okay. So what's a here? It's just aij. It's some antisymmetric matrix. Okay. That means that ij equals to minus iji. Okay, so this is some homework you can do yourself. So again, it's similar computation to the. So you do such computation for Gaussian integral, where you have just symmetric matrix. Okay, since you have here anti-commutation relation, so which means that psi, so this is equals to minus psi bar psi. So here we have, because of that reason, because of the anti-commutation, we have some antisymmetric matrix here. Okay.
Ilmar Hocam,
yes.
May I interrupt for a second? Since there are so many people who have joined after I made the announcement, so you can, if you have any questions, you can unmute yourself and ask your questions. You do not need to wait till the end of the talk.
Yeah, it would
Just
be
want to
better.
remind the people who have joined recently. Okay. Thank you. Sorry about the interruption.
Okay, thanks. Yeah, it would be better if you ask immediately, because then, so actually I'm finishing this Grassman story, so I'll start to talk about the coherent states. So again, maybe I need to give some motivation why I want to study Grassman variables, but still, again, these important mathematical tools which I need for motivation, for giving motivation about the Witten index. So I will use this Grassman algebra for the fermions. So, but later I'll talk about that. So just right now it's some mathematical background. So you really don't need to know what physics we have behind these structures right now. Just think about that, like mathematical objects. Okay, so we have some algebra with anti-commutation relation. Okay, and we want to study sort of calculus using this algebra. Okay, so how to integrate, how to take derivatives, and so on. This is the whole idea. Okay, if there's no any question, so again, this is some homework for you. Okay. Okay, now I'll stop here about the Grassman numbers. So just in my next lecture, and also in coherent states, I'll use this Grassman numbers. Okay. So what I need in order to compute the Witten index for the simplest models, I need to introduce the so-called coherent states. So again, there are many ways to compute the Witten index, but I'll try to roughly explain how to do that using path integrals. Of course, in 3 lectures to do all the computations is impossible, but still, with rough notations, I'll try to explain how to compute the Witten index. So for that, I'll use the coherent states. Okay, so probably you are familiar with that, but if not, just let me briefly remind you for coherent state for bosonic part of the story. Okay, so when you study harmonic oscillator, when you use this creation and annihilation operators, sometimes you introduce in the undergrad programs, sometimes you introduce the so-called coherent states. It's quite useful. So how we introduce the coherent state, it's just ein state of the annihilation operator. So let's say that we have creation and annihilation operators. Okay, so we have some algebra. So it's not so important right now. So I'm talking about the Heisenberg algebra, but still just think about it. You have some algebra. We have two operators. So let me think. So for A and A dagger, I don't need to put heads, but okay, let me right now put some head, but later it's not so important. But maybe for the fermions, I will keep heads. Okay, so we have some creation operators. So this is creation, and some annihilation operator. Okay, so it's, let me call it A like this. So this is annihilation. We have two operators, a dagger. Sorry, I wrote in a different way, but so this is annihilation, this is creation. Okay, that's not so. but to be correct, this physics literature, this is the creation, this is annihilation. So you'll see why it's creation, why it's annihilation operator. So now what we have this algebra. So so the commutation relation for A and A dagger is the following thing. So it's just equals to 1, and A with A equals to 0, A with A equals to A dagger, and this equals to 0. So what means this commutation relation? It means just A dagger minus A dagger A. Okay, so this is commutation relation. So for any A and B, the commutation relation means AB minus BA. Okay, so this is for all operators. So this is our algebra. So one can construct this realization of this algebra just by identification with the Fock space. Okay, with the so-called Fock construction. Okay, so how to do this Fock construction? So you start with some ground state of a so-called vacuum. Okay, so it's 0, and then our creation operator just creates from this state a new state. So you can act with a dagger to this ground state, and then you get a new state. Okay, and then you act with a dagger to 1 again. There's a square root. Yes. Okay, let me write square root here. Square root of 2, and there's another one. So yes, there's a question. Or is there a question? Okay. And so on. You can construct so states just by acting this creation operator. Okay. Now, but we are interested in the so-called coherent states. Okay. So here for all the states, of course, you know that I and J, it's just equals to delta ij. Okay, for all the states, you can check this yourself easily just using our algebra. So if you construct all states like this, then you can easily check. that if I, j are different, then the so maybe I can also put here some normalization. So then it's equals to 0, but no, there's also normalization. Okay, so this is equals to 1. Okay, so by the way, sorry, I didn't tell you. So this is what means this 0 is just it's just 0. Okay, so now what's the coherent state? Again, coherent state. As I said, it's the state which is a so we define this state as a state which has ion state of the annihilation operator. Okay, so now one needs to construct this state. So let's construct this state. So it's the way how we can realize this state. It's just let's call this our coherent state alpha. Okay, and then it's just the realization is the following. So it's e to the alpha a dega 0. So if you so if you define your state like this, then one can easily show that so A acting to this alpha. So again, the coherent state means that alpha is the ion state of the annihilation operator. So that means that you have just alpha and alpha again. Okay. So now how to show that for this is true. So let me expand this expression. So let's show that. Show this. Let me start with this alpha. So with this expression, dega 0. So let me so this alpha actually some number here. Okay. This is alpha some number. So let me expand this exponential. So this is just 1 plus alpha a dega plus 1 over 2 factorial. Okay, and then alpha a dega square and plus and other terms, and this acts on the vacuum. So then the 1x just gives the vacuum. Then you see we have such a term alpha a dega 0, and then 1 over 2 factorial alpha a dega square, and so on. So here you can easily see that it's just 1. Okay. So this is what's this state? So a dega acts on 0 gives 1. Another a dega gives square root of 2 So this gives just 1 over 2 alpha square root of 2, and here you have 2, and so on. Okay, so if you compute all this stuff, you'll get just 0 plus plus alpha 1 plus 1 over alpha squared over square root of 2, and so on. Okay. So this is our coherent state. Now, in order to check if it's really coherent state or not, what I need to do, I need to add this annihilation operator on the state and then see if I'll get to this expression or not. Now, so let me do this. So A acting on alpha gives, so let's copy this expression. And here A acts on this. And now what happens, so since it's an annihilation operator, it gives first term gives just 0, another one gives just alpha acting on 0, because again, here what happens, A times this one, this just gives 0, okay? And so on, okay? So then what we get alpha squared of, so what's this? So it's x on, this gives 0, this gives, no, sorry, it's just square root of 2. We don't have square root of 2. This gives just alpha square 1, and so on. And then just take out this alpha, it's just 0 plus alpha 1 plus, and so on, okay? But now it's again, you can see that it's again just alpha. And this equals just alpha. So in this state we call coherent state because it's really ion state of the annihilation operator. Okay, so ion state of annihilation operator. So this is the realization of the coherent state. Now, what's important for us to do again some analysis with this stuff. Maybe I don't know. I can show one more thing here, some computation, and then I'll move to the Grassman story again. So I'll just construct all this stuff just using this Grassman numbers now. But maybe it's important because later I'll use all these computations. Let me show a few things. So now, how to define this alpha? Let's say that, so we have, now this is our coherent state. This is our coherent state. So now, similarly to the creation and annihilation operators, what we can do the following. So let me call this alpha bar. Okay, and this I'll define like this. It's just alpha is bigger, and then one can easily show that this is just so this is just yes, it's just 0 and e to the alpha bar, so it's minus plus. Okay, it's just plus. We alpha bar and a dega. Okay. Sorry, no, there's no a dega we have. So here, so this is just e to the so this is e to the alpha bar a dega. Okay, and here it's just alpha bar a. So this one can check easily. This, so let me write the first one. So this you can check yourself. Then you can easily check that alpha bar with alpha, it's just e to the alpha bar alpha. Okay. But most important case, which I'll use later, but I will not show you. This is also some. Let me put homework. You can show yourself. So the important stuff. Let's say that we have some. Let's say we have some operator A, some operator, and let's consider such an integral. So you have integral d alpha d alpha d alpha bar is 2pi, and then e to the minus alpha bar alpha, and this is alpha a alpha, so alpha bar a alpha. This is just trace. Trace means that the sum of the diagonal elements of this operator A. Okay, so this is a trace of A. Okay, so this you can show yourself. So just use the definition of what's alpha and alpha bar. Then again, it's Taylor expansion. Put here and just compute this integral. So this is important. I'll compute this integral in case of fermions. Okay. So what means bosons and fermions right now? It doesn't matter. So this is sort of bosonic algebra now. I'll do the similar construction for the fermions. Okay. Now, if there's no question here, I can move to the fermions.
Ilmar, a naive question. For this formula to work, do we need any conditions on the operator A, or is it generically true?
In which sense? What?
I don't know. Like, do we need it to be diagonalizable, or like, do we need its spectrum to satisfy some conditions?
Just some operator from
just
theory.
Just any operator.
Yeah, any operator. Just take any operator. So and then so okay, you'll see that I don't use anything about this operator. So I'll do this computation for the Grassman. So it's a bit complicated. It's actually not so complicated. Even it's easier, but still, since it's less familiar for So in Grassman case, of course, we will not get exactly the trace, but we will get trace is minus 1 to the some sign is in front of A. But so I'll do this computation, and it's easy to see that I don't use anything about the operator A.
Okay, I see. Thank you.
So, but probably one needs to be careful when you work with this stuff again. But here it's still there's no any complicated stuff. Like in case of Grassman, I'll show you, because in Grassman you see here we have alpha bar and alpha, they commute, and then integration you can do the alpha or the alpha bar, doesn't matter. But later, in case of the Fermion system, it's important. One needs to keep this order in mind, or when you compute, and then there you have some sign. It's not sign problem actually. It's good that we have there some minus sign, but still. Okay, so now if there's no other questions, so let me construct the similar stuff for fermionic systems. Okay, so now so we can consider now algebra of the anti-commutators. Okay, so now let's say that we have some creation and annihilation operators. So actually, I still, so when I was preparing the lecture, I was thinking which letters I should use. I'm not sure. So if it's a good idea to use B and B dagger, but let's say that for fermions also. Now for anti-commutations, okay, let me try to use psi and psi dagger. I don't know. So because you'll see later why I need, since I write Lagrangian in terms of psi's, it's easy to use psi maybe. So okay, let's say we have another algebra. So it's, let me call just Fermionic algebra, whatever it means. Okay. So okay, Fermionic algebra. So it's some terminology which I just use, but it's not so important. Okay, so here instead of, so again, let's say that we have psi dagger and psi dagger and psi. So it's creation and annihilation operators. Okay, now instead of commutation relation, here we have anti-commutation relation. So that means that psi and maybe I should put heads, I don't know, psi. So this is operator, okay. So this equals to 1. That means that psi dagger plus psi dagger psi equals to 1. And psi with psi equals to equals to psi dagger, then equals to 0. Okay, so what's the difference here? Let's say that we start with some fermionic Fock space. So let's say that we have some vector 0. Okay, we act with this creation operator psi dagger on this vector or vacuum. So then we get some new vector 1. Okay, and if you act with annihilation 1, so to 0, that gives just 0. Now, the difference here that now you see we cannot construct any other state, because if you again act with this psi dagger to 1, that means that psi dagger square to 0. But psi dagger square, it's just it's 0. Okay, so and this gives just 0, because here it's, you see, it's just psi dagger plus psi dagger equals to 0. That means that psi dagger square equals to 0. Okay, so it's not possible to construct any state instead of, so it's we just have 0 and 1 here. Okay, so this is the realization of this algebra. We just have 2-dimensional Fock space, so 0 and 1 state. Now what we want to do, we want to now introduce again coherent states here. Okay, now again, what's the coherent state? We just start with annihilation operator. What we call the coherent state is just ion state of the annihilation operator. Okay, but now since we have some Grassman variables, this instead of alpha, which we had in the bosonic case, here we will have Grassman number. Okay, so it's important. So now this Grassman, the square of this number again equals to 0. Okay, now what's the coherent state? Again, the coherent state, it's just so we act So we add this psi to the, so maybe I should put here some, yeah, that's a bit always problematic. So because now I have this psi dagger, sort of psi head, this is operator, I act on coherent state, it's psi, so this is a state. Okay, again, don't confuse. So I'll put always this head on the, or maybe I, to not confuse, I can use phi. I don't know, phi. Let me use not psi but phi. Okay, maybe it's better. So then what I'll get, it's phi. So this phi, it's Grassman. Okay, phi. So this is Grassman number. So it's actually some complex Grassman. Now, again, how to construct this coherent state? It's this just similar construction. Okay, so the construction is the following. So again, here one needs to be careful about the order of the operators and also of the numbers. Okay, since we use Grassman numbers. So now, let's say that this phi, okay, it's just this our coherent state. So this is the construction. Okay, so this equals to it's similar to the Bose one. So it's just e to the now psi dagger. So with this psi dagger is creation, Grassman creation operator. Okay, now so it's phi. This is our coherent state. So what we need to check, using this construction, we need to check if this works or not. So now how to do that? Again, let's Taylor expand this stuff. So this is our phi, okay, equals to again, this construction we can Taylor expand. Okay, Taylor expand. Now, if we Taylor expand this, what we will get? We will get just 1 plus psi dagger phi. Okay, then plus other terms, but quadratic. But since psi dagger square and psi squares and other things, everything equals to 0, there's only zeros here. Okay, 0 term. So all other terms is just 0. So this acts on this vacuum. So then what we get, 1x on 0 just gives just 0 state. Okay. Now here we have psi dagger phi acting 0. So now, since these two guys, Grassman, psi and phi, so this equals to minus phi psi dagger. Okay, so that means that 0. So it's just minus phi psi dagger 0. So this operator, and this is just another state. It's just 1. So what we get 0 minus phi 1. Okay. So this is our coherent state. So again, what we need to check now, we need to check if it's ion state of the annihilation operator or not. Okay. So now let's write. So what we want to check, how acts annihilation operator on this state. So again, so now psi, this is our annihilation operator. Okay, so it acts on our phi. Okay, But now instead of phi, so here we know what's phi. It's just psi acts on 0 minus phi 1. Okay. Now, what it gives? So the first one gives just 0. This is equals to 0 because this is an annihilation operator. And then it's, okay, let me write minus psi phi 1. And then what I need to do, I need to commute this phi and psi. That gives just, this gives just plus phi psi head, okay? So this gives phi psi head and 1 here. But this is, again, this is since annihilation, but it gives just 0. That equals to phi 0, okay? Now, of course, it doesn't look that it's correct right now, but you see, since phi is a Grassman, I can always add phi square. I can add just 0, okay, to this equality. So what I can do here, I can add, so what I need actually, I want to get the following answer. So I want to get that this equals to phi times phi. This I want to get, okay? So in order to get this one, what I need to do, I need to add here some 0 term. Let me add it. So it's what I need to add, minus phi square times 1. So this actually, this is 0. And then let's take out phi. This is 0 minus phi acting on 1. It's acting, I mean, it's not operator, it's just Grassman number. So, and this is, of course, just phi. You see? And then I get just, I get that phi actually is ion state of the annihilation operator. And that means that this is coherent state. So this construction is a correct construction. Okay, now we have coherent state also for our Grassman, for our fermionic algebra. Okay, now here I'll show some nice formulas. Let me so again here the same. So maybe I should. So let me just write here. So to construct so we start this with ket states, and now to construct bra, what we need to do, just this is the same as in bosonic case. It's just e to the so it's important to keep order. So it's e to the phi and psi. So phi and psi. Okay. This like this. And then one can easily show that psi, so psi bar psi, it's just e to the phi. I'm sorry, why I use psi? It's confusing. Sorry, I'm sorry. You need to use phi here. So it's phi bar and phi bar phi. It's just phi bar phi. Okay. So this is easy to show. Maybe so now the complicated one, a bit complicated one, is the following one. So let's say that now we want to do the same computation which we did in bosonic case. But we want to compute the trace of the operator A. Okay, so this is or even okay. Let me even show first just some simple stuff. Then I'll compute the trace. Okay. So let me show first what's so let me show this identity first. Okay. So the second one. So this identity that this is identity operator. So this equals to so this equals to the phi bar d phi, okay, e to the minus phi bar phi, and then it's just d phi, so then it's just phi and phi bar, okay. So that what it means, that just acting to some state. So let's call this alpha, okay. No, alpha used for bosonic one. Okay, psi. Let's call psi. It just gives psi. This means this. Okay. Now, how to show that this is identity? Now, what we need to do, we need to tailor expand everything what we have here. So we need to tailor expand this one. So this is just 1 minus phi bar phi, okay, and we don't have any other terms because it's Grassman. This phi we compute here, it's just, you see, this is this one. This is 0 state, so the vacuum state minus phi times the 1 state, okay. So it's just here, if you write, it's just 0 minus phi 1, okay. So this is this term. And the another term you can compute yourself easily. It's just the same term, but now it's 0 and minus 1 and 5 bar, okay. So it's easy to compute this from here. So let's plug everything here. Then you have d phi bar, d phi, and here 1 minus phi bar phi, and let me open this bracket. It's just 0 0 minus phi 1 0 minus this 0 1 phi bar, and plus what's this, phi 1 1 phi bar, okay. So now if you open the last, so actually you see, whenever I have phi square, I don't need to keep this term because it's just 0 or phi by square. So I'll only keep terms with just non-zero terms. Okay, so now what I have here, 1 times this 0, this I have, and then 1 times so actually I don't need to also to keep terms just with 1 phi, but still, if you want, I can do this because integration will kill everything. Yeah, only some quadratic phi's will survive. Okay, so but still, okay, let me write all terms. So it's minus phi 1 0 minus 0 1 phi bar and plus phi 1 1 phi bar. So this is all, no, it's not all terms. And the last one, minus phi bar phi 0 0. So there's all others just zeros, okay? There's no any other term. Now, integration is just taking the derivative, okay? So if you take the derivative from this term, it's just 0. From this term, it will give the first derivative, it's not 0, but the second one, the d phi bar gives 0. This d phi gives 0. So we have only 2 terms, okay? So the first term gives just, you see, it's, if you take the derivative, it gives just 1, 1, okay? So because we take derivative first, derivative d phi, and then, so it kills this one, and the another one, d phi bar, kills the another one. okay, phi bar. So then here, you see here, in order to take the derivative, we need to write phi and phi bar in different order, and this gives 1 minus sign. And this, from here, we find that this just, what's that? Plus 0, 0. Okay, so now what we computed, compute that this is this integral, so it equals to this operator. Now, acting with this operator to something, you will see that it just acts as an identity operator. So this you can check yourself. It's easy now. It's because we have just two states here, 0 and 1. Okay. Now, so it's just your diagonal terms, 0, 0, and 0, 1, 1. There's no 0, 1, and 1, 0 terms. Okay. So everything equals to 0. So this is just identity. Now, using these techniques, now what we want to compute, what's the trace of some operator. Okay, so now just let me tell you that it's if you consider such integral, let's say like this one, so d phi bar d phi e to the minus phi bar phi, and here phi bar some matrix A, some operator A and phi. That's actually, it's not a trace. Okay, it's not a trace of the matrix A. So in order to get a trace, we need to put here minus sign. But later I'll compute also this term, this integral. So let me just put here minus phi. Okay. Now let's compute this one. Again, what we really need to do, we need to Taylor expand everything here. So the Taylor expansion of this one is again 1 minus phi bar phi. Then we need to Taylor expand this one. Okay. So normally what we had before, so we had this phi bar, it's just 0, so minus 1 phi bar. So now instead of phi bar, since I have minus phi bar, this gives just 0 plus, so instead of phi, I just write minus phi bar, so it's plus 1 phi bar, okay? And this is the same, so it's just 0 minus phi 1, okay? So if you plug everything here in this integral, what we'll get, so and then we need to open all brackets, so what we get, actually, let me just write the answer so you can check. So just plug everything in this integral, then, okay, maybe I can easily do this, I don't know. So it's just d phi bar d phi, so you need to open all brackets, so just let's keep again the first one, then second one just gives, so what's this? So it's 0, A, 0, 0, A, 0. So, okay, let me say like this. So I can, of course, write such a terms, but it's useless sort of. So I have 0, A, 0, and then what I have, for instance, this term. For instance, 1 phi bar A and 0, for instance. But this term, I know that it's useless. Why it's useless? Because when I multiply with this term, it gives phi bar squared, that gives 0. But if I multiply with this term, I just get 1 phi bar, but no phi. So integration will give 0. So this in any case will give 0. Okay, so I don't need such terms where I have just 1 phi. Okay, so then again, I have another one like this. So where I have 0. So 0. So what I have A and phi, and this is with minus sign probably, doesn't matter. So okay, this is also 0. This I'm not interested in this term. And then the last term, what I have minus, so what's this, phi, so it's 1 phi bar phi A and 1. So since it's phi bar and phi, it's just some numbers, I can take it out. Okay, so this is all my brackets. Now, so I again write this, the terms which I really need. So it's phi bar phi, and here what I have, it's just 0 A 0, and here minus phi bar phi 1 A 1. So of course I have other terms, but integration will give 0. Now, again, if I open these brackets, so it's d phi bar d phi. So 1 times this, the first term is just again 0 because of the integration. And what I have only these terms, phi bar phi 0 A 0, then minus phi bar phi 1 A 1. Okay, these two terms. Now you see I need to change the order of phi bar and phi in order to take the derivative. Then what I get just 0 A 0 plus 1 A 1, and that means that this is just trace of my operator. Okay. So this is the this is actually the way how you need to do all these computations in bosonic case. Just there, of course, you need to write the whole Taylor expansion, and then again get it back, sort of. Okay. Okay. So this is trace of A, and this is very important. Just I'll use this later. So the fact that here I have minus sign. So this is an important fact, okay? So this is important later for the boundary conditions for fermions and bosons, okay? Which boundary condition, periodic or anti-periodic boundary conditions I'll use. So just keep in mind that here in fermionic case, in order to get a trace of the operator, you need minus sign here. Okay. Now, let me show you the last computation for today. Now, what will happen if I'll just compute this without minus sign? Okay. So now again, if I write the same phi bar phi and e to the minus phi bar phi. So why I have this term, of course, you understand, because I have these terms here, coherent states. So in order to sort of to kill the term coming from phi bar phi, I need to e to the minus phi bar phi. Okay, so here what I have, phi bar A, so A some operator, and phi here. Now again, if I do all this, all these computations here, so that again very fast write down everything. So it's just 1 minus phi bar phi. Here it's just again it's 0 minus 1 phi bar, and here I have 0 minus phi 1. So if I open all brackets here, what I get d phi bar d phi. And what I have here, it's just 1 minus phi bar phi. And here, the same terms, okay, but with different sign now. So I have 0, of course, for the first term, I have the same sign, but for the next term, I have different sign. So here, if you remember, I had here minus sign. You see this sign, minus sign. Now, since I have here minus and here minus, so here I'll get plus sign, phi bar phi and 1 a and 1, okay. So I have, of course, two other terms, but they're equal to 0 if I will multiply this phi bar and phi with 1. If I will multiply, then integration will kill them. Okay, now what happens here if I integrate this stuff? Again, this is d phi. Okay, before integration, just let me write the last term. So what I have phi bar phi 0 a 0, and then plus phi bar phi 1 a 1. Okay. Now, if I integrate, what I get 0 a 0. Okay, and then minus 1 a 1. Okay. So you see, I have some different sign here. It's 1 minus sign here. Okay. Now this we'll call so this is trace of something. Okay. But now let me write in this way. So it's I'll call this is a trace of. So now it's not trace of the matrix A, but I'll write this in this way. So it's just 1 minus the f. So this is some Fermion number operator. So I'll explain what's that. So here, and I have A here again. Okay. So now, what's this f here? F. So f is so-called Fermion number operator. So so with you see how it will work. So this Fermion number operator, it has so for the vacuums, for the zero state, it's just it has ion value 0, and it has so let me write it this way. So let me write again this back. So this is trace of -1 to the f. So a. So this is again 0 a 0 minus 1 a 1. So how it works, this f. So for the zero vector, it has ion value f equals to 0. So this is the ion value of this operator. So, and for the one state, it has ion value 1. Okay. So now when you have -1 to 0, that gives just 1. So here you get just 1 because of this -1. And in case of this one vector, so what happens that it gives -1 to the 1, it gives -1, and here, so let me write this is just plus, and here just put -1. This is how it acts. So this is important for us. So again, so this object trace of -1 to the f, where we have some Fermion number operator, again, which gives so with eigenvalues 0 for the 0 state and with eigenvalue 1 for the 1 state. Okay, so this equals to d phi bar d phi e to the -phi bar phi, and here what I have phi bar a and phi. So this is important objects for us. So later we will use this in our computation in order to compute the within the index. Okay. Okay. So this is what I want to tell you about coherent states. So maybe but since I have a little time, maybe I'll start another lecture. But first, let me ask if you have questions or not.
Hocam, I probably missed how could we Taylor expand those operators?
No, the operator, no, okay. So again, the operator I keep as an operator. So this A stands just as an A, okay? But I Taylor expand states and I Taylor expand exponential. So again, so let me come back. So, so here, okay? So I use coherent states, okay? And then what's the coherent state? It's just a state which is the so it's the eigenstate of the annihilation operator. So phi phi here, this is annihilation operator. So okay, annihilation, and phi is the eigenstate of this phi. Of this psi of the annihilation operator. Okay, now. Then then you can ask how to construct this phi. So okay, you say that there is a eigenstate of our annihilation operator. Okay, nice. But how to construct this in terms of the the previous states like which we used in the Fock space. So this what we construct in also in bosonic case. You see this 0, 1, 2, and others. Okay, in case of the fermionic algebra, we have only 2 states, 0 and 1, because you cannot construct anything more. So here we showed that there's if you act with creation operator, you just get 0 and 0. Now this is the construction. Okay, so here we have e to the psi dagger phi, okay, acting on the vacuum state. Now this coefficient, of course, we can Taylor expand. Okay, we do this Taylor expansion. Okay, we expand not the state actually, but the coefficients in front of this. Okay, so then when you Taylor expand, at the end of the day, you just get that this phi, this coherent state, is equals to 0 minus phi 1. Okay, so this is the result. Okay, so this is a coherent state in our fermionic algebra. Okay, now whenever you see some coherent state here in any expression here, instead of phi, you can use again this this expression. You see 0, phi 1. Okay, so that's the idea. And whenever you have phi bar, then you use this expression. So again, for exponential, so e to the, so let me write it here, e to the minus phi bar phi, you just Taylor expand. Normally, it's just think about this phi bar phi just as an x. So then it just gives 1. Okay, then what you get phi bar phi, then you get 1 over 2 factorial phi bar phi square. Then you get minus 1 over 3 factorial phi bar phi cube, and so on. But since this is Grassman numbers, phi bar and phi, of course, all these terms equals to 0, because phi square equals phi bar square, and this equals to 0. So if you have such a term, phi bar phi, phi bar phi, that means that, okay, this equals to minus phi bar phi bar phi phi, but this, both of them equals to 0. So this equals just to 0. And also the higher orders, everything equals to 0. Okay. So now you expand this coefficient, then you write the formula for the coherent state, then just multiply everything. So these 3 terms, you just multiply, and then you need to multiply and then act on the state. So here just we wanted to show that this is just identity. Here, if you have some operator, you see again the operator. So I just keep this operator as so let me just put, so this some operator, so some number. So I have this operator here. I don't do anything. So it's just you see. Since here I get only diagonal terms of the A, that means that this is a trace of A. That's I don't expand the operator, but just expand sort of states. Okay, it's not expansion of states. Of course, I expand the coefficient in front of the state, and then it looks like expansion of state. So again, here you see when you expand the state, we get just 2 states, not more. But this is familiar because you see in Grassman, of course, here always whenever you have some expansion, you get just few terms and everything equals to 0 because it's Grassman numbers. Okay, again, when you expand bosonic part, of course, here in bosonic part you have a lot of terms. You see. So I mean infinitely many. So all terms entail expansion because alpha cube, alpha to the 4th powers, and all others, everything you should keep. So you have everything here. And again, when you, if you want to check this one, just here you need to write all. You need to keep all terms in Taylor expansion. Okay. But in fermionic case, we have just 2, 0 and 1, just with some coefficient. So that's the idea. Okay, I hope that's the answer to your question.
Thank you.
So, any other class? When I should stop? Actually, I should stop at 11.
Hocam, thank you so much for this talk. Is it okay to stop here?
Yeah, of course. I actually
Okay,
want to start a little bit about the second lecture. Okay. Mm-hmm.
Oh, okay, sure. Is there any questions? No question. Okay, all right. Then let me stop the recording.